Hello everyone, this is part 2 of section 2.2. Last time we left off with a third order linear differential equation with constant coefficients and finding its particular solution, so an IVP, and we saw how we generated 3 equations and 3 unknowns. So we'll look at another example. And first thing is to use the principle of superposition to find a general solution. We're already given the 3 solutions, and so if you want to say in general y is c1 y1 plus c2 y2 plus c3 y3, and we're using PS for principle of superposition. And then substituting the functions, we have c1 y1 e to the x plus c2 y2 is e to the x cosine x, and then plus c3 and y3 is e to the x sine x. So as we did before, we're going to have to generate 2 derivatives, and in order to do so, I think what I'm going to choose to do is recopy the c1 e to the x, and then from the second and third term, factor out an e to the x, and we'll have c2 cosine x plus c3 sine of x in parentheses. So that way we only have to perform the product rule once rather than the product rule on each of those terms separately. So therefore y prime would be c1, the derivative of e to the x, plus, okay, now we'll look at this factored form. First factor, e to the x, times the derivative of the second, and derivative of c2 cosine x, derivative of cosine is minus sine, so minus c2 sine x. We should really think the derivative of the argument x, but that's just simply 1, so not necessary in this case. And then plus c3 and the derivative of sine of x, cosine of x, and again, you can think the derivative of the argument, but again, that's just 1. And then by the product rule plus the second factor, so just recopy what's in parentheses, but first consider the derivative of e to the x is just e to the x, so that times what's in parentheses. Okay, and I'm just going to leave it at that, and then we'll do y double prime. Actually, you know what, it might be advantageous to simplify that first, would it be? And this is a c3 sine of x. Let me just leave it at that and do 2 product rules rather than factoring in e to the x. It's not really going to help tremendously. So I'm going to continue and do 2 product rules. So let me move it over a little bit, because then this is going to become a little bit lengthy. So I'm going to move it over here and try to fit everything in. First off, the derivative of c1 e to the x is again c1 e to the x. Okay, plus then we'll need the product rule on this guy. So first factor, e to the x, derivative of the second. Derivative of sine is cosine, so we get minus c2 cosine x, plus c3, the derivative of cosine is minus sine, so let's make that a minus. c3 sine x, then plus, okay, the second factor is what's in parentheses, derivative of the first, e to the x, just e to the x, so e to the x minus times the minus c2 sine x plus c3 cosine x. Right, and then I'm going to need need the product rule on this term. So plus the first factor, e to the x, derivative of the second, derivative of cosine minus sine, so minus c2 sine x, derivative of sine is cosine, so plus c3 cosine x, and then plus the second factor, so what's in parentheses, times the derivative of the first, but that's just the derivative of e to the x, which is again e to the x. So that times c2 cosine x plus c3 sine of x. Okay, now it may have been easier to factor out an e to the x from each of these and then perform just a single product rule, but choose to do it any way you like. But at this point I'm going to jump right to the initial conditions because the initial conditions, well, actually, let's simplify. Let's see if we can simplify this. This looks like we can simplify it. C1 e to the x. Okay, let's see if we get some common things. E to the x is out in front of everything, so let's see C2 cosines. Do I have any other C2 cosines? See, there's a negative one of them here. There's a positive one of them here. So they cancel out. And are there any other C3 sines? Yes, there are. There's this C3 sine over here. So get a different color. That C3 sine and this C3 sine vanish. And then we've got some common factors. The negative C2 sine with this negative C2 sine give us plus, or let's say minus 2. C2 e to the x sine of x. And then we also have this C3 cosine and this C3 cosine to make two of them. And so that'll be plus 2 C3 e to the x cosine x. Alright, so that made it a little bit simpler. And now for the initial conditions. Okay, y of 0 was given to be 1. So that's obviously from up here are the initial conditions. So y of 0 equaling 1 means that 1 is equal to, now remember that the cosine of 0 is 1 and the sine of 0 is 0. So that makes things a little bit easier because when we go to y, let's just go to the given the initial form. A C1 stays because that's e to the 0, but then the cosine of 0 is 1, and e to the 0 is 1, so we get C1 plus C2, but the C3 term goes to 0 because sine of 0 is 0. Alright, so we'll hold on to that. There's one equation with two unknowns. Y prime of 0 was given to be 0. So we have that 0 is equal to, okay, into y prime, C1, e to the 0 is C1. And then we get plus, the signs go to 0, so this C3 stays. And this sign goes to 0, so this C2 stays. Because cosine of 0 is 1. Alright, so there's another equation now with three unknowns. Let's see what we get when we go to y double prime to 0. So we get 0 equals, okay, let's go to this form, C1, and then just plus 2c3, because the sign of 0 is 0. Alright, so there's our three equations in three unknowns, and we can combine, let's see, I'll call this Roman numeral 1, 2, and 3, and let me move over here, and I think I'll take, let's see, what do I want to take? C1, let's take the first two equations, 1 and 2. If I use those, we got 1 equals C1 plus C2, and 0 equals, let's just reorder this, C1 plus C2 plus C3, and then if we multiply the top equation by -1, this just took me a few seconds to think about what would be the most advantageous thing to do, and this would be the most advantageous, because watch what happens here. You could solve them any way you like, as I said before. But now we get -1 is minus C1 minus C2, and line up to 0 equals C1 plus C2 plus C3. So now what happens is the C1 and the C2 actually cancel out, and we just get -1 equals C3. So that was an advantageous way to proceed. So now let me take C3 and go back to equation 3, because I have just 0 equals C1 plus 2C3. So C1 plus 2 times -1. So then C1 would be a positive 2. And then we'll go back to equation 2. Actually, I can go back to equation 1 again, or 2, doesn't matter. Let me go to 1. 1 equals, because all I have left to solve for is C2. So 1 equals C1 plus C2, so 1 equals 2 plus C2, and C2 would be a -1. Okay, so there's the three constants. So then our particular solution would be y equals C1, which is 2 e to the x, plus C2, which is a -1, so minus e to the x cosine x, and then plus C3, which is also a -1, so minus e to the x sine of x. Excuse me. Okay, so again, three equations, three unknowns, often generated, and choose whatever method you like to solve them. All right, a little more theory. Talking about general solutions of homogeneous, we already saw linear combinations, so basically the same thing. We're saying in equation 3, that's referring to the initial equations that we started this entire section with. So just flashing back to it, this associated homogeneous. So any linear combination is a solution. That's what Theorem 4 is saying with regards to a general solution to a homogeneous. But then if we start talking about non-homogeneous, okay, a non-homogeneous, as we stated, is of this form. So that's taking equation 2 from the first page. And we said it has this associated homogeneous. So remember, it's basically because it's a function that it's equal to it's non-homogeneous, and when it's equal to 0, it's homogeneous. So if we let y sub p be a particular solution to the non-homogeneous differential equation, and y is any solution, then, and that's uppercase y, then if we say y sub c is equal to whatever any solution is minus the particular solution, then we say that y sub c is a solution to the associated homogeneous equation, because we're subtracting the particular solution from a general solution. And so it would follow that, just adding the y sub p to both sides, that our general solution is the sum of what we're calling y sub c and this particular solution, y sub p, that's going to be a solution to the non-homogeneous differential equation. Now, from Theorem 4, we'll call y sub c the linear combination of solutions to the associated homogeneous, where all the y's are linearly independent solutions to that associated homogeneous. And so, therefore, we're going to call y sub c the complementary solution. So y sub c is going to be the solution to the non-homogeneous differential equation. So it's the complementary solution of the non-homogeneous differential equation. Okay, so then Theorem 5 talks about solutions to non-homogeneous equations. And we're going to let y sub p be a particular solution of that. And then, there's a bunch of mathematical formalities here, but these are the solutions, these y's are the solutions to the homogeneous. And if y is any solution, then here's y sub c plus y sub p. So a quick summary of all of that theory is basically that y equals y sub c plus y sub p is a solution to the non-homogeneous, where y sub p is the particular solution of the non-homogeneous, and y sub c is a solution to the associated homogeneous. So here we want to solve now differential equations that are non-homogeneous when we're given the complementary and particular solutions. So the general solution, because it's, again, non-homogeneous, because it's equal to some function. In this case, it's just a constant, but it's not equal to 0. So a general solution is going to be y equals y sub c plus y sub p. And so we're given that y sub c is c1 e to the 2x plus c2 e to the negative 2x. And we could have actually solved that by creating the associated homogeneous and then characteristic equation, factoring, and we already had the real root theorem. So that would be very simple to show, but they gave it to us. But then this is plus the particular solution, which is given to be negative 3. So let's say just minus 3. So this is a general solution to the non-homogeneous. And to find the particular solution, we're going to have to find just one derivative, because it's only second order. So the initial conditions are given with respect to the function and its first derivative. So here we'd have c1 derivative of e to the 2x, 2e to the 2x, so 2c1 e to the 2x, plus the derivative, c2 tags along, derivative of e to the negative 2x is negative 2, e to the negative 2x, and then the derivative of the constant negative 3 is 0. So then we go to the initial conditions, and y of 0 was given to be 0. So then we have that 0 equals c1 plus c2. Don't forget the minus 3, because either the zeros go to 1, but that minus 3 tags along. And then the second initial condition, y prime of 0 was given to be 10. So then we'd have that 10 is equal to 2c1 minus 2c2. Okay, so then there's two equations with two unknowns. Here's what I'm going to do. I'm going to move this 3 to the left, so I'll make it 3 is equal to c1 plus c2. Then just to make this one simpler, I'll divide by 2, because 2 is common. So 10 equals c1 minus c2. By doing that, we already have c2, coefficient of c2 equal but opposite. So 8 is equal to c1, and so c1 is 4. And then if we back substitute into, you could use either one of the two equations. I'll use this equation, 3 equals c1 plus c2, so 3 equals 4 plus c2, and c2 is negative 1. So, excuse me, then we get our particular solution, y is equal to, okay, back up here, c1, which was 4, e to the 2x, plus c2, which is minus 1, so just minus e to the negative 2x, and don't forget to tag along the negative 3. Okay, so second example, we again start by forming a general solution to the non-homogeneous. Oh goodness, this is, I'll have to change the file here, because I have the same problem. So this is not the question we wanted. The question we wanted is this. Y double prime minus 2y prime plus 2y equals 2x. And the initial conditions with that y of 0 is 4, y prime of 0 is 8, and the complementary solution is c1 e to the x cosine x plus c2 e to the x sine of x, and the particular solution is x plus 1. Alright, so I apologize for that, but actually I'm going to change that on your notes. So that's going to be question number 2 on your notes. And so therefore we would have, for a general solution to this, again it's non-homogeneous because it's equal to a function of x here, going to be y sub c plus y sub p, and we're given them. Y sub c was c1 e to the x cosine x plus c2 e to the x sine x, but then plus y sub p, which was the x plus 1. Okay, so again, we're only going to need one derivative to make this easier in terms of the differentiation. Let's factor out an e to the x from the first two terms. So we'll have e to the x times c1 cosine x plus c2 sine of x. And then don't forget the plus x plus 1. Okay, now it's derivative, y prime. First factor, e to the x, derivative of the second, derivative of cosine minus sine, so minus c1 sine x. And again, we really should think derivative of the argument x, but that's just 1, so no need to write that. And then plus c2 times the derivative of sine of x, which is cosine x. Alright, that's just the first part of the product rule, plus the second factor, what's in parentheses, derivative of the first, but the derivative of e to the x is just e to the x, so therefore it's just e to the x times, then recopy what's in parentheses, the c1 cosine x, plus c2 sine of x, and then the derivative of x was plus 1, and the derivative of the constant 1 would be 0. Alright, so that's all we need. And now we can go to the initial conditions. And the first one was that y of 0 is 4. So then we get that 4 is equal to, okay, we're going to y, we're substituting x is 0. Remember, cosine of 0 is 1, so it looks like c1. But sine of 0 is 0, so the term containing c2 goes away. And then we have plus x is 0, so that's gone. But don't forget that plus 1. But this one unfolded rather neatly, because now immediately we see that c1 is 3. And so the second initial condition, y prime of 0, was given to be 8. And so then we have that 8 is equal to, okay, going to y prime, the e to the zeros are 1s, sines go away and cosines stay. So sine of 0 is 0, that's gone. c2 cosine of 0 is c2. And then for this term, cosine of 0 is 1, so the c1 stays, and the c2 goes to 0, but don't forget we got this plus 1. So then we have that 7 is c2 plus c1, but we already know c1, so 7 is c2 plus 3, and c2 is 4. Okay, so then we can form our general solution. Y equaling, go back up here, c1 was 3, so 3 e to the x cosine x plus c2, which is 4, so plus 4 e to the x sine of x. And then don't forget to tag along this x plus 1, which was the particular solution. Okay, so we're going to stop this video right there, and we'll come back with the final third part on a special, very special method called reduction of order.